Hey, welcome to Passages in Applied Mechanics by Dr. Lorenz Garcia. Today, statics, tensile stress. Mechanical design depends so much on the proportionality of the pull to the stretch in the tensile loading of elastic materials, as one of the major concerns of us, as engineers, is the estimation of the ability of engineering materials to withstand conditions such as tension, compression, torsion and bending without failure or excessive deformation. In the applied mechanics, the strength of a material is its ability to withstand an applied load without failure or plastic deformation. Therefore, the field of strength of materials deals with forces and deformations that result from their acting on a material. A load applied to a mechanical member will induce internal forces within the member called stresses when those forces are expressed on a unit basis. The stresses acting on the material cause deformation of the material in various manners, including breaking them completely. Deformation of the material is called strain when those deformations too are placed on a unit basis. The stresses and strains that develop within a mechanical member must be calculated in order to assess the load capacity of that member. This requires a complete description of the geometry of the member, its constraints, the loads applied to the member and the properties of the material of which the member is composed. Let's introduce some fundamental concepts then, such as stress, strain and the factor of safety in the context of elastic behavior of engineering materials in tension. Tensile strength. As we said, strength is the ability of the material to withstand applied force without failure. As such, strength is one of the most important mechanical properties of engineering materials. Strength varies, depending on the nature of the load applied to the material, and we often have to distinguish between tensile, compressive and shear strengths of a particular material. The tensile strength of a material is determined by the tension test, which consists of the gradual application of an axial tensile force until fracture occurs. Typically, the testing involves taking a small sample with a fixed cross-sectional area, and then pulling it with a tensometer at a constant strain rate until the sample breaks. Much engineering design is based on this measure of tensile strength, known as ultimate tensile strength, UTS, which is defined as the ratio of the maximum tensile force applied before fracture occurs to the initial cross-sectional area of the test specimen. Tensile strength plays a crucial role in engineering applications as it helps determine the suitability and reliability of materials for specific tasks. Engineers rely on tensile strength data to ensure that structures, components, and materials can withstand expected loads and forces without failure. By understanding the tensile strength of different materials, engineers can make informed decisions during the design and manufacturing processes. Typical average values of ultimate tensile strengths are 470 Newton over square millimeters for mild steel, 150 for aluminum and 70 Newton over square millimeters for nylon. Tensile strength is a critical property in numerous industries and applications. In structural engineering, it ensures the safety and stability of buildings, bridges, and other infrastructure. In the automotive industry, tensile strength is essential for manufacturing reliable and crash-resistant components. Moreover, it is vital in aerospace, manufacturing, construction, and even everyday consumer products, such as ropes, wires, and textiles. Direct axial stress in tension. If we consider the behaviors of materials under loads which do not cause rupture, crushing or any form of permanent damage or deformation, we must learn how to calculate the allowable load on a structure or a component which will ensure a sufficient degree of safety. It is what we call as direct stress, which is the intensity of force distribution over the cross-sectional area of the material subjected to direct load, and defined as. The international system unit of stress is the Pascal, which the symbol, Pa. The definition of the Pascal follows from the definition of stress, which is force per unit area, or equally, Newton per square meter. Factor of safety. It is interesting to compare the result of the stress with the ultimate tensile strength of the material. For example, let's consider we have a bar of mild steel subjected to a tensile force of 20 kilonewtons. By applying the formulae, it will give us a stress of around 100 megapascals, which is far below of 500 megapascals the mild steel has as UTS. Obviously, the stress is not sufficient to rupture the material of the bar, and therefore, the bar is safe under the applied load, but, how safe? If we compare the UTS and the actual stress in the material of the bar as ratio, it is. This ratio is an indication of the degree of safety considering the fact that the actual working stress in the material is considerable below the ultimate tensile strength. Thus we say that the factor of safety in our example is equal to 5. Therefore, one of the definition of the factor of safety, Fs, is the ratio of the ultimate tensile strength to the actual working stress in the material. The higher the number of factor of safety, the safer the product or structure is. An factor of safety of 1 indicates that a structure or component will fail immediately when the design load is reached and will not be capable of supporting any extra load. Structures or components with factors of safety less than 1 are not acceptable. If the consequences of failure are severe, such as loss of life or physical injury, a higher factor of safety will be required either by design or by law. A factor of safety increases the safety of people and reduces the risk of failure of a product. When it comes to safety equipment and fall protection, the factor of safety is extremely important. If a structure fails, there is a risk of injury and death as well as a company's financial loss. The safety factor is higher when there is a possibility that a failure will result in these things. Buildings commonly use a factor of safety of 2.0 for each structural member. The value for buildings is relatively low because the loads are well understood and most structures are redundant. Pressure vessels use 3.5 to 4.0, automobiles use 3.0, and aircraft and spacecraft use 1.2 to 4.0 depending on the application and materials. The field of aerospace engineering uses generally lower design factors because the costs associated with structural weight are high. For instance, an aircraft with an overall safety factor of 5 would probably be too heavy to get off the ground. This low design factor is why aerospace parts and materials are subject to very stringent quality control and strict preventative maintenance schedules to help ensure reliability. A usually applied safety factor is 1.5, but for pressurized fuselage it is 2.0, and for main landing gear structures it is often 1.25. Axial strain in tension. If a material is subjected to direct axial load, its size is changed in the direction of the applied force. A member subjected to a tensile force tends to stretch. It is found that for a given magnitude of tensile load, the elongation produced is proportional to the length of the member. The elongation per unit of original length is what we call axial strain, and it is a convenient relative measure of the change in the longitudinal dimension. If the total elongation produced in a member is designated by x, and the original length by L, then the axial strain, E, is Hooke's law. All solid materials exhibit some degree of stiffness, or the ability to resist deformation under load. Load extension diagrams recorded during tensile testing of materials all indicate that in order to produce elongation, a force must be applied. Furthermore, the greater the force, the greater the amount of elongation produced by that force. The property of stiffness is closely related to the elastic and plastic behavior of materials. It is found that up to a certain point, known as the elastic limit, the material can be stretched without taking up any permanent deformation. It can be said that within the elastic limit, the material possesses the property of elasticity, or the ability to return to its original size after the force has been removed. If, after the material is stretched to its elastic limit, the force continues to increase, the material ceases to be elastic and displays plasticity, which means, it will suffer permanent deformation until eventually rupture occurs at what we already know to be the ultimate stress. A further observation reveals that there is another limit, known as the limit of proportionality, within which the elongation produced by a tensile force is directly proportional to the force. The concept of proportionality between load and elongation of elastic materials date from 1676 by the famous English physicist Robert Hooke. He first stated the law as a Latin anagram. He published the solution of his anagram in 1678 as ut tensio, sic vis, meaning As the extension, so the force, or the extension is proportional to the force. In its original form, Hooke's law simply stated that for a bar of elastic material of uniform cross-section, subjected to a progressively increasing tensile load, the elongation is directly proportional to the deforming force. The mathematical equation expressing Hooke's law is: the constant E, relating the stress and strain, is a measure of a material's ability to resist stretching, within the limit of proportionality, and is sometimes appropriately described as the modulus of stiffness. The stiffness of a structure is of principal importance in many engineering applications, so the modulus of elasticity is often one of the primary properties considered when selecting a material. A high modulus of elasticity is sought and deflection is undesirable, while a low modulus of elasticity is required when flexibility is needed. Another application of stiffness finds itself in skin biology. The skin maintains its structure due to its intrinsic tension, contributed to by collagen, an extracellular protein that accounts for approximately 75% of its dry weight. The pliability of skin is a parameter of interest that represents its firmness and extensibility, encompassing characteristics such as elasticity, stiffness, and adherence. These factors are of functional significance to patients. This is of significance to patients with traumatic injuries to the skin, whereby the pliability can be reduced due to the formation and replacement of healthy skin tissue by a pathological scar. The modulus of elasticity can be determined experimentally. Typical values for common engineering materials are 200,000 megapascals for steel, 70,000 for aluminum, or 12,000 megapascals for timber. Let's apply these concepts to solve engineering problems. Dr. Lorenz Garcia here, thanks for watching. Ciao.